Hello! Talk more about functions today. We talked last time about function basics, and here we'll give some application examples with gases, and we'll talk also about classes and give some more examples as well. I'll first go to the class website, click on functions and gases, and then download my IPYNB and open it in my Jupyter notebook. And yeah, like we mentioned last time, functions are used to organize code, and they can be very powerful in simplifying your code and making it so you can use that calculation method over and over again. Here's the ideal gas law. As chemical engineers, you'll, if not already, will be very familiar with it. PV equals nRT. And I've written it here in terms of molar volume so that liters per mole, or in this case for SI units, cubic meters per mole, and our universal gas constant in joules per mole Kelvin, and temperature in Kelvin. So we can define a function with the def statement, and then we name it pressure underscore IG, for example. We can give it default values for temperature as well as molar volume. And here's our return statement. Returns our pressure for a given temperature and molar volume in Kelvin and SI unit, meter cube per mole. We can also write this in one line. We're using a lambda statement. This can be helpful, and so you need to understand how the lambda function works. You set the variable, and this becomes your function name. You can call against this. So I've got lambda, and then I give it my variables for which I need to provide it a value, or can provide a value, and then I set a colon. I can also specify default values, and Rg times T over mv. It's the same as above, and then running these two, I can get the pressure with the default value, so I don't need to give it anything in the function, and we'll return a pressure, an absolute pressure, or I can give it a new temperature, and it'll use the default molar volume. And so there's that example. We can also calculate our pressure given a volume and the number of moles, and we just calculate a molar volume and then feed it into our ideal gas pressure. So I have a 1 liter vessel with 1 mole of gas. 1.001 cubic meters divided by 1 mole at 300 Kelvin yields this absolute pressure. One of the course outcomes is to use algorithms. An algorithm is just a method or a recipe, and a good definition of an algorithm is a function. And we'll need to make order of magnitudes estimates. You do that as an engineer all the time. So here, for a demo we'll do in class, but you can think through it here as well, is estimate the number of moles inside of a balloon given the class temperature and the class absolute pressure. The approximate pressure inside the balloon is about 3/4 of psi, and you can write a function to do that, where you can rearrange your ideal gas law. It's one way, and we'll also talk about other ways to do that. So here I've got a plot of the ideal gas pressure as a function of molar volume. This can be very helpful to plot your relationships that you develop or are given. And here we use the matplotlib package. So I import that, and we specify 2 arrays or 2 lists. It will convert it to an array inside of matplotlib, and I've got at least I believe that's true. That could be false, but here I've got an array of molar volumes, and then I'm going to specify 3 different temperatures, and for each of those temperatures I got a loop, and I'm plotting in my plot, plt plot, lines of pressure for each given temperature, because temperature is listed first in my function, right up here, temperature given first, and then my molar volumes And this is an array of molar volumes, and so this will create an array. I label it. I can do my fprint statement, which is kind of cool. And so it'll print out this each is a temperature. In this case, the first one is 300. So it'll label it 300K, as you see right here. I can put a horizontal line for the atmospheric pressure at our elevation here in Provo. And then I label the axes and give a legend and show the plot. So this this kind of a procedure or steps to create your plot will be repeated by you multiple times going forward in your career using Python. So as we stated above, we could calculate the number of moles or estimate the number of moles in a classroom or another volume. And instead of creating a function, I instead want to solve this equation. So back up here, if I give it a pressure, I want it to calculate the number of moles. So I can give a pressure and a volume and a temperature and then calculate for the moles. I can rearrange the equation easily, but sometimes that's not straightforward. So here we're going to use the fsolve. This is something that you need to be familiar with, and so we're introducing it here. We'll talk about solving equations in the future, but this is a very straightforward, hopefully, application of fsolve to solve for the number of moles given the volume, the pressure, and the temperature. So I create a function. First of all, you'll need the SciPy package. So to install your packages, once again, you go to your environment here under environments, under Anaconda. You can click here and open a terminal, and then just pip install SciPy. And here I've already got it installed, so it will say it's already satisfied. But that's a way to install that. Then I create a function where I'm trying to get a root. So if you remember from your high school classes, most of you took classes where you're solving the quadratic equation. And this is similar to that in that I have a function that gives me a pressure, and I want that pressure to equal my classroom pressure by varying my molar volume given my temperature. So my lambda function includes a variable molar volume, and my classroom temperature I'm using in the function to stay constant. And then this function, when this function equals 0, that's my molar volume at that condition. And so I stick that function into the fsolve, easy as that, and give it a guess value, and it will solve the molar volume. So there's my molar volume, just what we expected. And the number of moles of gas in the room is just that classroom volume divided by that molar volume. And we can check it using PVNRT. And we could have done this at the front, but using a function, that's why I say it's fairly straightforward. And fsolve, you can get the same answer. So I also wanted to demonstrate here the ideal gas law written so that if you give it any variable or any two variables, it'll calculate the third one. So if I give it a temperature and a molar volume, it'll give a pressure. And the way I'm doing that is setting default values of none for all three of them. And then if P is none, I'm going to use the other two to return the pressure. So here's our RT over V will return our pressure. And similarly, if we don't give it a temperature but give it the other two, or molar volumes but give it pressure and temperature, it will calculate the molar volume. This try and accept is powerful in that it will try to do something. If there's an error, it goes into the accept block. And in this case, there may not be enough information because you didn't specify, or the person didn't specify a molar volume, or they didn't specify a temperature. So if we run that, and I didn't run these up above. Let me run these up above so this will work. should work. Volume is not defined. Let's see if we can debug this. Oh, maybe all the way back up here. Here's my 1 liter. So I've got for my 1 liter, this volume, I can specify temperature and my molar volume like I did above, and it will calculate a pressure in pascals. There it is. And the moles of an ideal gas at a given pressure and temperature inside the classroom. As I solve my ideal gas, give it pressure and temperature, it'll return a molar volume, invert that and multiply it by my volume, give me the number of moles, and there's that. So hopefully that example is helpful to demonstrate the variability or power of functions, where depending on what you feed it, it will give a different answer. Another equation of state beside the ideal gas law is the van der Waals equation. It's one of the oldest ones after Boyle's law or the ideal gas law. Here we have the exclusion volume, B, and the attractive portion. And we have parameters for oxygen, methane, and water here. We're going to use it for methane, so I can specify my function, my van der Waals function. And for methane, I can type this in and convert it from liters up here to my SI units, including in Pascal. So that's this conversion here. And then I'm going to just plot the two of them. The van der Waals and the ideal gas, you can see at higher densities or lower molar volumes, this is a log-log plot, it deviates from the ideal gas law as we would expect. Another example for classes. Here we have, let's say we have multiple tanks, and in this problem we have a bunch of tanks. 12 tanks, and they're different shapes. And we have different levels in each tank in our factory, perhaps. And let's see, this looks like we got spherical tanks with these levels, cylindrical tanks with these levels, conical tanks with these levels. And all of the tanks have a diameter of 2 meters except for the spherical tanks. And they're filled with biodiesel. Calculate the total volume of fluid in the tanks given the level. So, how are we going to solve that? We have to relate the level and the shape to the fluid volume. So here is one way to do it, in that using classes. So I give it a max capacity for each tank, a shape of the tank, the default value, and this is the documentation for that parameter. We got a diameter as well as the level in those tanks in meters. And then I can define a fluid volume given a specific shape and its diameter and level. Easiest one is with the cylinder. Pi d squared over 4 is my cross-sectional area of the cylinder. And I just multiply that by the fluid level. That'll give me my fluid volume in cubic meters. And sphere's a little bit different, but that's fairly straightforward to calculate. There's the equation. And my cone is similar to my cylinder, but it's a third of the volume. And then I can just create in this case, a list of levels for my spherical tank, and then create an array of objects for each of those levels. And then for my cylindrical tanks and my conical tanks, and then I just loop through each one of those tank types and sum up the total volumes for those fluid volumes. And there's my result. Oh, I've got to run my class setup. 228 cubic meters of biodiesel I have in those tanks. And you can inspect some of the lists of the objects for the cylindrical, and here I've got spherical tanks. You can also refer to each individual object within that spherical tank list and refer to its level, for example, or we can call the fluid volume. And there's that fluid volume for that specific tank. Hope these examples were helpful, and you can take time to look through those and make sure you understand. God lives and loves us.